Okay, we're going to come back and take a look at Lexis diagrams. So here's a Lexis diagram. Here is the year, here's age, and we're going to look at a particular cohort. We're going to zoom in and take a look at this cohort. There were lots of people born in here. Some died young, unfortunately. Some lived for a long time. So we have lots and lots of people in this birth cohort. I've zoomed in a little bit. Okay, and so we have some long-lived people. We have some people who really lived for a really long time. Here's something we can do. Each of these lines represents the entire person's life. We know when they were born. We know when they died. In this particular cohort, we can count up, number one, we can count up all of these people who were born in this cohort. I think I did a little calculation, a little rough approximation a little while ago that said that there were, what did I say, 80 million people born in any year across the world, roughly. So we could imagine sometime in the past, and there are just millions of these lines. One of the things we can do is we can count up the lengths. Count up the lengths all of this cohort's lifelines. We can get the total length of each of these lines. Some lines are pretty long. This person lived way out here. This person unfortunately died young. We can add up all of those years. We have all these people across the bottom. And so each of these, the total of this are called the person years lived for this cohort. So we call that the cohort. We sum up all of the lengths. Those are the cohort person years lived. So each of these lines represents how long a particular individual in that cohort lived. We've added up them across all of those individuals. We know how many were born. So if we take the cohort person years lived and we divide that by the number of people in the cohort, that will be the average number of years lived for that cohort. The average number of years lived for that cohort, that's also, we can call that the average age at death for that cohort. All we did was we added up the lengths of all of those lifelines. That gave us the total numbers of cohort person years lived. And then we divided by the size of that cohort. That's the average age of death for that cohort. We have another name for that. We call that the cohort expectation of life at birth. And earlier we called that thing E0. We can do some related things here. So suppose instead of counting from birth, we call it, in this particular instance, we counted from birth. That's why we called it E0. I'm particularly interested in, for my birth cohort, let's pick a number out here. This is, say, the age 65. I'm interested in the expectation of life, of remaining life at age 65. We do essentially the same thing. We count up how many of these lifelines cross age 65. Remember, I said that a horizontal line at age 65 is a border. Then we can count the lengths of each of these lines for this cohort after age 65. And then we can divide by the number of people who made it to age 65. And so that's how we would calculate expectation of remaining life at age 65 for this cohort. Okay? We just add up the lengths of everything above age 65. So this is a conditional expectation of life. That's the years of remaining life for those people who reached age 65 from this birth cohort. Let me, can I do this? Can I erase? Can I do that? Maybe I can. Let's see. Does that work? Almost. Almost. Oh no, I erased the lines. Okay. Let me go back here. And I'm going to add in a bunch of those lines again that were unfortunately deleted. Okay, we have a bunch of these lines out here like that. Okay. Here's something else we can do. We can calculate the number of person years lived in a particular period of time. So periods are vertical slices. Okay. And we have more people here. We have some people who actually died in the middle of this period that we're looking at. Some people who lived out here and died out here. Some people who were did this, and then some people who were born in this period, and then they lived out to there. Actually, we're going to add one person here who died, was born in this period and then died in that period. Maybe we'll add one more here. Unfortunate person who was born and died in that period. Now, what we can do here is for this period, we can count up the lengths of the lines that cross that period. This person was born back here, lived all of his life through, died out here. That person lived all the way through that period. So did this person. This person only lived that much. This person lived this much, and this person lived this much. All the rest of these people lived all the way through this period. What we can do is we can add up all of the lengths of the lines in that period, and that's something that we call the period person years lived. So we have a cohort person years lived, and then for a vertical strip, we can calculate the period person years lived. Now, the other thing we can do is, there are many of these lines, of course. Just like the cohort person years lived, what we can do is we can calculate a period person years lived by adding up all of those lines. Now, how many lines were there? the number of lines that went through that period is going to be the population in that, the number of people who lived during that period. The number of lines is the number of people. And we can calculate the total number of person years lived, just like we did for the cohort, except we're doing it for a vertical strip. Now, why do I do all of this? It's because I'm now going to be a formal presentation, as I promised, of the birth rate and the death rate. And I called this thing lowercase b, and I called this thing lowercase d. Before, I was I was trying to skip over exactly what went into the denominator. I'll be more explicit right now. The birth rate b is the number of births that occurred in the period divided by the period person years lived. And D is obviously going to be the deaths in that period divided by the period person years lived. So that's our formal definition. Our denominators are not persons. Our denominators are person years. And by talking about the period, what we're talking about is the number of years lived in a vertical strip. Sorry, that must have been distracting. We are going to continue. I'm going to start a new topic using this Lexis diagram. What we're going to do now is we're going to talk about the cohort life table. The cohort life table is one of the most famous models, demographic models, and it summarizes a lot of information. We're going to go through that. You've probably seen some of this before. We're going to do it. We're going to try and do it relatively quickly. There is a period life table. In addition to a cohort life table, where there is a period life table, it turns out that if you understand the cohort life table, then there are very, very, very few changes that you need to know in order to understand the period life table. So we're going to do it with the cohort life table first. It's a little bit easier. It's a little bit more straightforward. But once we explain it, then you'll be able to understand what goes into the period life table. You guys may have seen this before, a life table. We're going to use X for age, and I'm going to do an abridged life table, so we'll do it by 5-year intervals, so 0, 5, 10, 15, 20, and so on, up to, say, 100 years old. There are certain columns of the cohort life table. Let me just write down some of them. There's going to be a column called the LX column. I'm going to use the subscript notation. Sometimes when we talk about a continuous version of it, I'll try to use the functional notation. So I may later use the L of X kind of notation, but right now I'm talking about a discrete set of variables at a particular age X. So I'm going to use this L subscript X notation. There are a couple of more columns that I'm going to explain. We're going to use this funny notation at lowercase subscript n dx. I'll explain what that is. These are the deaths between, in a particular age group. There's going to be an nqx, which is our probability of dying, and npx, which is 1 minus the probability of dying. It's going to be the probability of surviving. Now that we know what a person year is, in this case, we're going to talk about N capital LX. That's going to be a column of person years lived, and we're all going to use that in order to get to an E sub X, which is our expectation of life. So this is where we want to get to. These are the columns of the cohort life table. I may talk about one or two more, but those are the columns of the life table that we're going to concentrate on. And now, how do we get to there? We're going to start with, I think we're going to start with actually a Lexis diagram. We have a Lexis diagram. This is a cohort life table, so we're going to start with studying a cohort. As I said before, we have lots of people in this cohort. Some of them die young. Some of them live for a long time. This person died young. This person lived a little bit longer, but then died. This person lived for a very long time out to there. Okay, so as we had before, this is age, this is our time, our year. So these are all of our people in our cohort. Each of these is a lifeline. Each of these is a lifeline that tells us how long each person in our cohort lived. And what we're going to do is we're going to follow our birth cohort over their entire life. And it's possible to see everybody. There's no one who's missing. There's no one who moved out. There's no bad data. Let's presume that we have a complete count of everyone in our cohort. Okay? And now what we're going to do is we're going to redraw each of these. And what I'm going to do is I'm going to take each of these lifelines and I'm going to do two things. The first thing is I'm going to sort them. I'm going to take each lifeline from our cohort and sort them from short to long. And what I'm going to do is I'm going to draw them over here as like a histogram. So here are the short ones. This is the first one over here. There's a short one. This person unfortunately died quite young. Then there's another one who lived a little bit longer. And then here's another one. And then there's another one. And we keep track of all of these. This is the first person. This is the second person. This is the third person. This is the fourth person. Suppose in our original population we had, say, 2,123. Then way out here we have the longest lived person, the one who lived to be 100 years old or whatever. And that is going to be the 2,123rd person. So we have sorted all of our lifelines from short to long. If we count in this way, if we number in increasing direction from 1, 2, 3, what we're doing is we're counting the deaths. If we number in the other direction, so we had 2,123. If we start out here and counted 2,123, and then 2,122, and then 2,121, all the way down to 1, if we count it in this direction, then what we're counting is the number of people still alive. And this one is the number of people dying. I guess they would be dead. We've ordered them by death. So we have age up here. We could say how many people made it to age 20. And then this person unfortunately didn't. But this person, all the people after this, they all made it beyond age 20. We could ask the same thing about age 30 or age 40. Okay? So the important thing is that each of these lines is sorted from short to long. So this, we could, if we were to connect all of these lines, maybe it went like this, all the way out like this. If we connect all of those lines, then it gives us the shape of our 2,123 people in our original cohort. Actually, often, rather than keep track of the actual numbers, what we'll do is we'll keep track of proportions. So sometimes what we'll do is we'll track the proportions of the people still alive. Proportions of those still alive from the original cohort and so we'll call this 100% or 1, and then this one would be 0.99 I guess 94 or something, and then this is down to 0. Okay, so we can set the left side to be 0 and the right end at 1. And if we do this, if we're talking about proportions, then we set this thing at 100% out here. In some life tables, that's actually set for a number like 1,000 or 10,000 or 100,000. And then they'll just count proportions. We're going to set in at Berkeley, we always set that left side at 1, so that these numbers are all proportions. And this number that we set the left side at is so important. It has a special name in demography. It's called the radix. The radix is the base counting down at Berkeley. We almost always set the radix at 1, so it's 100%. Notice that just as we saw before, if we added up the lengths of all of these lines and divided by the number of people divided by the radix, then that gives us the average length of life, which is the expectation of life at birth, E0. So adding up each of those lines and dividing by the radix is going to give us the E0. Now, it turns out that in demography, we don't actually typically draw the picture this way. I know. What we typically do is we flip it. So we have, right now we have the number of people, or the proportions, on the x-axis, and we have age on the y-axis. We're going to flip that. And in demography, we typically do it like this. So we have the proportion surviving, and we have age here, and we just said we set our radix at 1 at Berkeley. And now we're going to draw these lines exactly like this. We're going to copy this, but we're going to now flip the axes. And so we have the short line there and another short line. And then our lines start to get a little bit longer. And so it's horizontal like that. And then down here we have some lines. Remember, because they were all sorted out here, and then we have our last person out here who lives out to there. Okay? It turns out that we hardly ever draw the full horizontal line. In fact, we actually just typically, we just keep those little dots and then we ignore the lines. Let's see, can I do it like that? Okay. And then what we do is we connect those dots by a smooth line. Okay. And when we do that, we're now talking about this curve, but we should remember that underlying that curve are all of those horizontal straight lines. This curve we refer to as the survivorship curve. And this is, we describe that, we give it a name, survivorship, and we give it a symbol, and that symbol is our L sub x, or sometimes we're going to use that L, that functional notation L of x rather than the L sub x. The key about this is that the LX curve is monotonic. It goes down, it never goes up. It may be flat, but it is monotonic. So this is important. This monotonicity. Notice that if our radix was 1, we could ask, okay, so here's 1/2, this is 0.5. We could ask, at what age are half the people still alive? And then, so that's our age. We can calculate the median age of death in this population. That's a horizontal line at the 50% mark. If we took a vertical line, and suppose we have a specific age, and our age is, say, age 10, we can take a vertical line. That number right there is L sub 10, and it tells us the proportion of the population still alive at age 10, that is the survivorship to age 10. So L10 is either the proportion still alive at age 10 or the survivorship to age 10. So that is actually the very first column of our life table. That is this one, the L sub x. Okay, so now we know how to calculate L10, and we could count down here and find out what age 0.5 of the people are still alive. Let me give you a couple of quick factoids. And if you were born in the United States at the beginning of the 20th century, so 120 years ago, so in the U.S., 1900, 120 years ago, L1 was around 0.95. So L1 is survivorship to age 1. This proportion still living at 1 year, and that was about 0.95, so 95%. So it meant about 5% of babies died in the first year of life. So that was a lot. It turns out that in that around 1900, L20, give or take, the probability or the proportion of the birth cohort that lived to age 20 was about 0.9. So 90% of them made it to age 20, 10% of them died before age 20. And L65, no, I have L60, was about approximately 2/3, around 0.66. Today in the United States, L1 is 0.995, so quite a bit better. L20 is around 0.99, and L60 in the United States today is about 0.9. So today in the United States, we have about the same survivorship as we had survivorship up to age 20 in the year 1900. I guess I should make a comment that today in certain, I think the worst, highest infant mortality places in the world right now, roughly 10% of babies die before age 1. So I would say that in the highest mortality places in the world, L1 right now is around 0.9. So that's some facts to put this into context. Here is a typical shape for human beings of the LX curve. And it is, because there's infant mortality, there's a sharp drop in the first year or so of life, and then it flattens out for a long time, and then when you get to be out by my age, all of a sudden things go bad, and then it gets steeper and steeper until everybody is gone. Okay, so this is a typical shape of the LX curve. It's high up here at 1. It starts at 1. Our radix is 1. There's infant mortality. Then it's flat for a long time. And then you reach some age, and then things happen and people die. So now here's age X. Here's age X plus N. So this is L of X, and here this is LX plus N. Okay? It's always monotonic. It drops quickly over far on the left side. There's a long period which is plateauing, relatively flat, and then at old age, there's a sharp decline. Let's give a quick zoomed in picture. We're going to zoom in on this area from LX to LX plus N. N could be 1 year, it could be 5 years, it could be 10 years. It doesn't matter at this point, but I just want to look at a zoomed in picture of it. So I'm going to draw this again. Here's my X. Here's my X plus N. As I said, for most ages, in the middle, not at the very young, not at the very old, it's relatively flat. So I'm just going to draw it like this. Here's LX. Here is Lx plus n. And we can draw this. Here's our age. What is the difference now between this and this? So we have the survivors at age L of x. We have survivors at age Lx plus n. That means that this distance must be the deaths that occurring between age x and x plus n. So that is this distance here. So deaths between ages x and x plus n, that's that vertical red spot. That is going to be, you can see it, Lx minus Lx plus n. That's this height. This is L of x. This is L of x plus n height. So that difference is L of x minus L of x plus n. And we call that n dx. And that's the numbers of deaths that occur between ages x and x plus n. And that is going to be the second column of our life table. And let me talk about this notation at the moment. Whenever you see anything, if you see notation that looks like n something x, it refers to events occurring between ages x and x plus n. These are the n years after age x. It is an interval n years wide. So the n refers to the width of the interval, the x refers to the starting age of the interval, and now I should say, when you see something that looks like something sub x, like L sub x, that refers not to an interval, but to a point in time. And in this case, it's going to be the age x. Okay? Exact age x. So here is our example, n dx and L of x. N dx is our second column, and it refers to the numbers of deaths that occur between ages x and x plus n. I'm going to only talk about two more tonight. It's night for me. I'm going to ask, what is the probability of dying in the interval, in the age interval x to x plus n? Well, you can see it now. That should be the numbers of people dying in that interval x to x plus n divided by the people who started off that interval. So this is the numerator is the deaths that occurred in age group ages x to x plus n, and then this is the number of people alive at age x. So let's look at our picture again. We're going to take the difference between this is ndx, and we started off there. That's how many people were at risk of dying. We count that, and then so that is going to be ndx divided by lx. It is so important, this number is so important, we give this a particular name and symbol, and this is called the probability of dying in age group x to x plus n, and we call that nqx. That's a q. We call that nqx. It's the probability of dying in the interval x to x plus n, conditional on having been reaching age x. So this is a conditional probability. I should say that, that's NQX. That is this column of the life table. This one. And let's see, NDX we said up above. What did we say NDX was? NDX was L of x minus Lx plus n. So that is L of x minus Lx plus n divided by L of x. You can see that is 1 minus L of x plus n divided by L of x. And so what is L of x plus n divided by L of x? These are the survivors to age x plus n. These were the survivors at age x. So that is the probability, given that you lived to be age x, that you would still be alive at age x plus n. So this piece is, so the probability of dying is 1 minus this piece. This piece there must be 1 minus the probability of surviving to age x plus n, given that you reached age x. So once again, this is a conditional probability. It's the probability that you will make it to age x plus n, given that you had made it to age x. So we call this thing L of x plus n divided by L of x is just as important as the probability of dying. This was the probability of dying. We gave that a symbol. So we are going to call that the probability of surviving to age x plus n, given that you had made it to age x. The probability of surviving, we give that a symbol as NPX. NQX is the probability of dying, NPX is the probability of surviving. I'm going to draw a box around that. I'm going to draw, let's see, a box around this. And that is the next column of our life table. Where is it? There it is. NPX is right there. And I think I'm going to stop right now, and we'll continue this over the weekend.